what you do is your generating function would be a sum of, say, Jn of x t to the n, or t to the n over n factorial, whatever you want it to be. In fact, you might want to put an n factorial there. So then you write down, you express Jn of x as an integral, and then inside the integral, you can do that you sum up the series. So I guess we're not going to have any video for a while. So let me just give you some definitions. These are definitions about singular points of differential equations. And so what we've got is a differential equation of the form y double prime of x plus, say, p of x, y prime of x plus q of x equals 0. Now, if y double prime is finite for all x, I'm sorry, not for all x, but if it's, and I left something out. This is a, of course, y of x, because this is a linear homogeneous equation. So if y double prime is finite when y prime and y are finite, then at some particular point, then we say that that's a regular point. So x0 is a regular point. If y double prime of x0 is finite for all finite y prime and for finite y prime of x0 and y of x0. So that's the definition of a regular point. It's what you'd say is a normal point. On the other hand, if y double prime is infinite when y prime and y are both finite, then we say it's a singular point. And then there are two kinds of singular points. One kind is and of course, if y double prime is infinite, the reason it's infinite for y prime and y finite is that p or q would be infinite. And what we'd say is that there are different kinds of infinities here, because suppose x minus x0 times p of x0, or p of x, let us say, if this remains finite as x goes to x0, in other words, if p diverges as 1 over x minus x0, and if q of x times x minus x0 squared remains finite, then we say it's a regular single point. And the essential singularity is when you just can't get y double prime to be finite, essentially, no matter, or at least not under these conditions. So this says that q may diverge as 1 over x minus x0 squared, but not worse than that. So that's basically these are basically the definitions of regular point and regular singular point, or non-essential singular point. The other case is an irregular singular point or an essential singularity. Sometimes one treats the point at infinity, one considers the point of infinity, and in other words, one might ask, as x goes to infinity, do you have a, or minus infinity, do you have a, does y double prime remain finite or not? And in that case, what you do is it seems to be working.
Yeah, momentarily. I'm not quite sure. If you touch anything, I'm not sure what will happen. But
So you're saying let's give it a few more minutes.
it looks like it's going to work for now.
Is this the same one you used that we used before?
Yeah. I'll get another one. I thought we had another one, but
Yeah. Well, as I said, I was near the Apple store yesterday, and I was wondering.
probably trying to get exactly the right one. Because there's Apple over a few years they changed their display.
Yeah. Well, let's get the right one.
Yeah.
So where are we? We're way early here. Okay, so these are just the definitions again that I was going through. Let me see if I can use the pointer, and that'll allow me to stay near the screen and the blackboard. So to treat the point of infinity, you set z equal to 1 over x, or x equal to 1 over z, and then you take these derivatives and turn them into z derivatives. And then what you've got is that if these two quantities remain finite, then as z goes to 0, and then x goes to plus or minus infinity, then x0 equal to infinity is a regular point. If they don't remain finite, but on the other hand, with one less power of z, they do remain finite, then that's a regular, then the point of infinity is a regular singular point. Otherwise, it's an irregular singular point. So those are the definitions, and Legendre's equation provides an example. If we divide through by 1 minus x squared, then Legendre's equation takes this form, and you see that x equal to plus or minus 1 is a singular point. On the other hand, you can show that it's a regular singular point, and also at x equal to infinity, it's a regular singular point. So, those are some of the definitions. And the next topic is one that's very important in physics, namely Frobenius's series solutions. And this, oh, fuck. I mean, this is really disgusting. All right, let's just forget about the goddamn computer. Let me just call Tom and tell him, well, I can tell him later. He's obviously not going to do anything about it. So let's see, power off. I assumed that he had this under control, and consequently that I would be using the screen rather than the blackboard. So what Frobenius did was something that you've probably seen in your quantum mechanics classes or in your UNM classes. Namely, if we rewrite the differential equation like this, so if this is our differential equation, and what we're talking about is, notice, second order and homogeneous. So there's no term on the right-hand side that's a source term independent of y. And it's second order, and of course it's linear. So what Frobenius did is write this as x to the r, write the solution as x to the r, and then a power series, n going from 0 to infinity, some coefficients. And then he showed that one could solve for the coefficients, and one could solve for x to the r. And notice what's going on here. A0 is the coefficient of the lowest power of x in the solution, and the lowest power then is x to the r. Offhand, we don't know what that is, but what we do is we substitute this into that differential equation, and so we differentiate this twice and put the result here. We differentiate once, put the result here. We take the whole sum and put it there, and then we get a differential equation with lots of terms. In particular, y prime is the sum r plus n, a n x to the r plus n minus 1, and y double prime of x is the sum r plus n minus 1, a n x to the r plus n minus 2. So we substitute these three series into this differential equation, and that then gives us, and see now I am going to have to use this board way over here because I should have written on this board. Anyway, let's start with this board. So we substitute that in there, and then we get this differential equation. Sum n equals 0 to infinity, n plus r minus 1 plus n plus r p of x plus q of x, a n x to the n plus r equals 0. And now this equation must vanish for all x, and if it vanishes for all x, if it must vanish for all x, then the coefficient of every power of x has to vanish. And so that means what we have is n plus r n plus r minus 1 plus, well, in order to see this, what we have to do, of course, is to substitute the values of p of x and q of x. Now, if p of x and q of x are simple polynomials, which they are in most of the differential equations that we study, then we can identify what the different powers of x are in this equation. And we can also find the value of r, because this has to be true for all x, and in particular x equal to 0. If we set x equal to 0, the only thing that survives, or the lowest term, the lowest one that survives here is going to be a0, and that would give us the equation then n plus r minus 1 plus n plus r p of 0 plus q of 0 times a0 would have to equal 0, but a0 is by definition not equal to 0. And so we get this equation, and this is a quadratic equation for r. So we solve for r this way. And this is called the indicial equation. And of course, like any quadratic equation, it has two roots, r1 and r2. And to analyze higher powers of, find the coefficients for higher powers, what we do is we, of course, sum p of x. We write it as pj x to the j equals 0 to infinity, and q of x equal to sum j equals 0 to infinity qj x to the j. Here I'm expanding everything about x equal to 0. One could equivalently expand about any point on the real line, but it's the notation is simpler if we just have expand about x equal to 0. Otherwise, we have x minus x0 to the j and x minus x0 here to the j. So we substitute these two into this equation, and then we say that the coefficient of every power of x has to vanish. And what that does then is give us a recursion relation. And let me see if I can do this right this time. So the recursion relation, so we're saying the coefficient of every power of x vanishes. That gives us a recursion relation. The recursion relation is a sub k is minus 1 over r plus k minus 1 plus p0 plus q0 times the sum j equals 0 to k minus 1, j plus r times p k minus j plus q k minus j, and each of these combinations multiplies a sub j. Notice this sum goes from j equal to 0 to k minus 1, and so that gives us the value of a sub k. So we solve this one at a time and get the coefficients. So I think I'll do some examples in detail, because the way you come to understand this is by seeing examples, I think. Although you probably have seen this in a discussion of the hydrogen atom or other things in quantum mechanics class, I would hope. Anyway, the case for the equation y double prime plus omega squared y equals 0, well, you know the solutions of this harmonic equation are sines and cosines. So here we have p of x equal to 0, and q of x is equal to omega squared x squared. That is to say, after we've written this equation in the form x squared y double prime plus omega squared x squared y equals 0. The initial equation then is r minus 1 equal to 0, and so the roots are r equal to 0, and r2 is r equal to 1. And so then when you solve this equation, what you find is that y of x, for example, is, well, first I should maybe write down what the recursion relation is. It's a sub k is equal to minus q2 ak minus 2 over k minus 1, and this is then minus omega squared a k minus 2 over k minus 1. So it's a very simple recursion relation, and consequently, if a sub 1 vanishes, then a sub 3, a sub 5, and all the odd ones vanish. So for the first root, r equal to 1, what one gets is that y of x is a0 cosine omega x, and if you, this is for r1 equal to 0, r2 equal to 1, what we get is y of x is equal to a0 over omega sine omega x. So we get the usual solutions, cosine and sine, from Frobenius' method in this case. Now what happens is you can apply this to many other cases, and in particular we can look at Legendre's equation. And what we'll do is we'll rewrite Legendre's equation as x squared y double prime plus xp y prime plus qy equal to 0. And here p of x is minus 2x squared over 1 minus x squared, and q is x squared lambda over 1 minus x squared. And here the Legendre equation that I'm looking at here is 1 minus x squared y double prime minus 2x y prime plus lambda y equal to 0. So this lambda is a sort of eigenvalue. So one could apply Legendre's equation, I mean Frobenius' method directly, but it's actually simpler to just substitute the power series expansions for y, y prime, and y double prime into the differential equation. And then after some chugging, what you get is aj plus 2 is equal to j plus 1 minus lambda over j plus 2, j plus 1, aj. Now, if you look at this for large j, what you see is that aj plus 2 is going to be effectively the same as aj. Because if you divide through by j squared, you see that this is 1 plus j to the minus 2 minus lambda j to the minus 2 over 2 plus j to the minus 1. 1 plus j to the minus 1 times aj. And so in the limit j going to infinity, aj plus 2 is almost the same as aj. So you've got then a power series that looks like this. The sum effectively x, it's effectively x to the j for large j, and so that's a series whose a series that diverges. And so the conclusion then is that if you have a solution that's sensible and doesn't diverge, then this series has to terminate. And of course it terminates if lambda is equal to j plus 1. And so that's the statement that the eigenvalue lambda has to be an integer times an integer plus 1. And then one finds the Legendre polynomials, and these of course are described in more detail in the later chapter of the book. Now, the success rate of Frobenius' method was analyzed in detail by someone named Fuch, and he proved various theorems. Let's see, I've used all of these, so let me go over here. So what we have are the conditions. Fuch showed us what conditions, under what conditions Frobenius' method will work for second-order differential equations. And he had 3 results. First of all, and they all depend upon the roots of the indicial equation. And so the first statement is, if R1 equals R2, then Frobenius's method gives just one solution, not 2. Well, that's sort of obvious because the way you find the 2 solutions in general is you work out the case of R1, and then you work out the case of R2. If they're both the same, you're only going to get one solution. The second result was that if R2 is equal to R1 plus some integer, n, I'm sorry, some non-integer, some rational number, then you get 2 solutions. The third thing that Fuchs proved is that if R2 is R1 plus an integer, then the bigger root figure R1 or R2 gives a solution. So the bottom line, and this is if you're expanding about a regular point or a regular singular point. So this is if you're expanding y of x equals x minus x0 to the r, sum j equals 0 to infinity, aj x minus x0 to the j. If you're expanding, if x0 is a regular point, so this is if x0 is regular or regular singular point. So so the bottom line then is, if you expand about a regular point or a regular singular point, then you get at least one solution. And if you look at, if you go back to the Legendre equation, what you find is that the two roots lead to the same solution. And so that's an example of number 3. All right, so maybe there are questions, because I'm about to start a slightly different topic. So I guess I'll use that board there, which is a little bit clearer than the other boards. So the idea here is differential operators. Let's look at x to the n. ddx. This room is apparently designed for giant professors. I guess they have a basketball team in mind. Anyway, let's consider what this is. Well, x to the n, d by dx to the p acting on that. What you get is k factorial over k minus p factorial, and then you get x to the n here, plus k minus p, because you differentiated p times. And so if you imagine doing a reflection, x goes to minus x, you see that this goes to minus 1 to the n plus k minus p times k factorial over k minus p factorial x to the n plus k minus p. And in fact, okay, so that's what happens when you reflect x to minus x. And so what you can say is that the differential operator x to the k d by dx to the p has parity minus 1 to the n plus, well, minus 1 to the n plus p, n minus p. But whether it's plus or minus doesn't matter, because we're talking parity. In other words, in a differential equation, this differential operator, if you reflect x to minus x, you get minus 1 to the n minus p, apart from whatever effect it has due to the x to the k. And so, if you have a differential operator like L of x equals h0 of x plus h1 of x times d by dx plus h2 of x d2 dx squared, then if we do a reflection on that, we get L of minus x is going to be h0 of minus x minus h1 of minus x d by dx plus h2 of minus x d2 dx squared, using this rule here. And so what we can, now there are a couple of obvious definitions. If L of minus x is equal to L of x, then we say L of x is even, or just L is an even differential operator. If, on the other hand, L of minus x is minus L of x, then L is odd. Now, those aren't the only two possibilities, and in fact, in general, a differential operator of second order isn't going to be even or odd. But on the other hand, as you may have noticed, if you take any old function, the function f of x, it will not be either even or odd, but you can rewrite it as 1/2 f of x plus f of minus x plus 1/2 f of x minus f of minus x. And now this function is even, and this function is odd. So you can write any function as the sum of an even function plus an odd function. And so too, you can write any differential operator as the sum of the even differential operator plus an odd differential operator, using the same trick. So, so you can decompose any differential operator into an even one plus an odd one. It turns out that in physics problems, the differential operators are often even. They often have H2 is often equal to just 1, in which case the thing is even. Any questions? So now here's something a little bit more subtle. Suppose we have a solution to the differential equation L of x, y of x equal to 0. And suppose L of x and L of minus x are well defined. Then if this equation is true for all x, we also have, we can set x equal to minus x, and we'll have the equation L of minus x, y of minus x is equal to 0. So now here's the subtle point, you see. If L of minus x is equal to plus or minus L of x, that is to say, if the differential operator L of x has definite parity, in other words, is even or odd, then what you can say is that this is equal to plus or minus L of x, y of minus x. But this says then that if the differential operator has definite parity, and if y of x is a solution, then y of minus x is the solution. So let me write that down. So if L of minus x is plus or minus L of x, and L of x, y of x is 0, then L of x, y of minus x is also equal to 0. So if you have a differential operator of definite parity, even or odd, and you have one solution, you get, by reflection, a second solution. So this, the solutions to your differential equation come in pairs. And what you can do is arrange them to have even or odd parity, because you can say y even is going to be y of x is going to be proportional to y of x plus y of minus x, and y odd is going to be proportional to y of x minus y of x. And so, since y of x and y of minus x are both solutions, since the equation is linear, their sum and difference are also solutions, and one is an even solution, the other one is an odd solution. And as I said, you I think, have seen or will see in quantum mechanics class when there's a discussion of the hydrogen atom, in particular, you have the angular equation, and you'll have solutions that are even or odd under reflection. These are the spherical harmonics. Okay, any question? The next topic is something really quite cute, and this is something that someone by the name of Wronski invented. And what's cute is, first, imagine that we have a bunch of functions, y1 of x, if you can find constants k1 through kn such that y1 through yn satisfy this equation for all x, then these things, the y's, are linearly dependent. So dependent. You see this concept of linear independence and dependence that I emphasized when we were talking about linear algebra. It resurfaces again and again in mathematics and mathematical physics. We can differentiate this I times, and then we get the ith derivative we'll get that all of them are going to be 0, and if we define a matrix yij equal to the jth y, and the I minus first derivative of the jth y, then and then we take the determinant, that's called the Wronskian. So the Wronskian is the determinant of y of x, the matrix y of x, which is to say the determinant of yj, I minus 1, I labeling rows, and j the columns. So this is a Wronskian and vanishes on an interval if and only if the functions yj or their derivatives are linearly dependent on the interval. So that's the Wronski's idea. Now, in this n-dimensional case is sort of complicated, but there's a much simpler case, namely in the case of a second order differential equation. So second order linear homogeneous equation like that. If y1 and y2 are two linearly independent solutions, then the Wronskian doesn't vanish. The Wronskian then being y1 of x, the determinant y1 of x, y2 of x, y1 prime of x, y2 prime of x, then this is not equal to 0. And of course it's equal to y1 of x, y2 prime of x minus y2 of x, y1 prime of x. And we say this is not equal to 0, except perhaps at isolated points. You can then take the derivative of the Wronskian, and if you take the derivative of the Wronskian, let's see, maybe I'll go to that board over there because it's easier to see. So if you take the derivative of the Wronskian, then what you get is W prime is equal to Y1 prime, Y2 prime, plus Y1, Y2 double prime, minus Y2 prime, Y1 prime, minus Y2, Y1 double prime. Now you can see there are two terms that cancel, this one and that one, and so this is just equal to Y1, Y2 double prime minus Y2, Y1 double prime. But now, if these are solutions of the differential equation, then we can say that W prime is Y1, the minus sign, P Y2 prime plus Q Y2, and then plus Y2 P Y1 prime plus Q Y1. So we get this equation for the Wronskian, and once again we get a cancellation, namely the Q terms cancel, and so what we get is minus P times Y1 Y2 prime minus Y2 Y1 prime. But that's just the Wronskian. So in other words, it's equal to minus P W. So now we have a differential equation for the Wronskian, and it's W prime is minus PW, and so you can integrate that. That's ddx of log W is equal to minus P. So log W, apart from a constant, is minus the integral of P dx, let us say dx prime up to x. And if that's the log of W, then W of x is e to the minus integral up to x, P of x prime, dx prime, apart from an overall constant, which I'll maybe stick there. But actually I've got the overall constant in that we could integrate from a lower limit. And in fact, the constant actually is W of x is W of x0 to the minus integral x0 to x of P of x prime dx prime. So this actually is Abel's formula. And he, by the way, only lived to be 27 years of age. So he was rather precocious and unlucky. Anyway, so this is our formula for the Wronskian. So in other words, the Wronskian, which is the determinant of, which is a certain determinant, which I explained over there, it has a solution that just depends upon p, one of those coefficients. And so now if we remember what the Wronskian is, well, it's y1, y2 prime minus y2, y1 prime. Well, we can rewrite that as y1 squared times the derivative of y2 over y1. And so if the derivative hits y2 prime, to y2 you just get y2 prime, and that gives you this term. And then if you differentiate y1, you get the other term. So this is a differential equation for the ratio of the two solutions, namely d by dx of y2 over y1 is the Wronskian, which we already know just from the differential equation. In other words, what's p of x over y1 squared. That is to say, we just divide both sides by y1 squared. And now, this is something that we can integrate. In fact, it's kind of a trivial integral. It's that y2 of x is equal to y1 of x times an integral up to x w of x prime over y1 squared of x prime dx prime plus a constant. So in other words, let's combine what Fuch said, namely if you apply the method of Frobenius to a second-order linear homogeneous differential equation at a regular point or a regular singular point, you're always going to get one solution. Now you use Wronski's trick and you automatically get a second solution. And this second solution, you can see, is just in general linearly independent of the first solution, because it's the first solution times a constant plus the first solution times an integral involving the Wronskian and y1 squared integrated. So I suppose there could be cases where they're linearly dependent, but that would be a remarkable coincidence. So now, in fact, if we recall what our formula is for the Wronskian, we can rewrite the second solution explicitly as y2 of x is y1 of x. Again, apart from an overall constant here, in fact, we typically don't want the part of y2 that's proportional to y1 because that's a linearly dependent piece. We would have this as an integral up to x of e to the minus integral up to x prime of p of x double prime dx double prime divided by y1 squared of x prime dx prime. So you have to do two integrations. You first find out what the Wronskian is, then you integrate it over y1 squared, and you get the second solution. So, in the case where P actually vanishes, you have y2 of x. So if P is equal to 0, y2 is y1 of x, simply times an integral dx prime of y1 squared of x prime, dx prime over y1 squared of x prime. So we always get two solutions. Questions? All right, so now I'm really out of blackboard space unless I go to the backboard there. And check the time. Okay, we've got about 14 minutes left. So let's go to the backboard here. You might say, well, how do we know we don't have three solutions? So suppose there were three solutions. Yj double prime plus Pyj prime plus Qyj equal to 0. So that's a Yj, there's no prime here. And suppose they were linearly independent. In that case, we could say that the Wronskian which is the determinant, this determinant would not vanish if these were three linearly independent solutions. On the other hand, each of the double primes, each Yj double prime is just minus Pyj prime minus Qyj. So this is Y1, Y2, Y3, Y1 prime, Y2 prime, Y3 prime, and we'd have minus P Y1 prime minus Q Y1 minus P Y2 prime minus Q Y2 minus P Y3 prime minus Q Y3. So I see I should have written these spaced out more. Is it obvious what this actually is? Let me maybe rewrite it slightly. Y2, Y3, Y2 prime, Y3 prime. Okay, well you can see that this is obviously 0 for all x, and the reason is that the third row is a linear combination of the first two rows. And remember when we studied determinants, if any row is a linear combination of the other rows, then, or linear, or proportional to any other row, if two rows are proportional to each other, then the determinant vanishes, and in particular, in this case, the determinant vanishes. So that means then that for a second-order differential equation, apply the method of Frobenius to a regular singular point or a regular point, you get one solution. Wronski's trick gives you a second solution, but you can't get a third linearly independent solution for this reason. You can extend these, or at least this argument, to an nth order differential equation, and then you find that if you have an nth order differential equation, you can find n linearly independent solutions, but you can't find more than n linearly independent solutions to an nth order linear homogeneous differential equation. So I can go stop there for that particular topic. Now the next issue is boundary conditions, and boundary conditions are of course, extremely varied. You can have the functions vanish at the start of the interval, the end of the interval, somewhere in the middle of the interval, or you can have the derivatives vanish at the start, at the end, somewhere in between. So there are many, many different kinds of boundary conditions. But basically, what you do is you can say that if you have a second-order differential equation, then the general solution is A y1 of x plus b y2 of x, and you can solve for A and B by applying boundary conditions. And I think you've done that many times if you had in other classes. And if you have an nth-order differential equation and you have n solutions, then you use n boundary conditions to determine the n coefficients. All right, I don't think I'll go into that any further. The next topic is one that has a lot of implications for physics, namely it's a variational problem. And so let me ask, is there a question? Remember, I have candy and I can give you candy to ask a question. So let's define something that we can think of as kind of like an energy functional. An integral from A to B, e of x prime squared of x plus q of x u squared of x dx. So this is a functional. That's why, if I had done this correctly, I would have written, the text is correct. Technically, one uses square brackets for a functional. So E is a functional because it maps any function into a number. And the number is an integral, well, it's this integral involving P and Q and the function in its first derivative, integrated from A to B. And so we might ask, what U's extremize E? So that's the question. And the way we analyze that is we look at, and what we mean here by extremize is what makes it either a local maximum or an absolute maximum or a local minimum and so forth. And so what we imagine is that if we're at a maximum or a minimum, whether it's local or not, then the variation of E, when you make a small change in U, this variation will be zero to first order in the small change delta U. So in other words, just delta, the change in the number, E of U, is then an integral. We have the change in this, well, that's going to be it's going to be P times 2U prime, change in U prime, and plus Q times 2U, the change in U, and this is all going to be integrated dx from A to B. And of course, the change in U prime is the same thing as the that is to say, the change in derivative of U is the same thing as the derivative of the change in U. We can integrate by parts, and if we do, what we get is the change in E of U, skipping a couple of steps which are in the text, we get minus P u prime prime, that's integrating this term, and then we get plus QU, and that multiplies delta U dx, and then we have the boundary term, which is for boundary terms, which is PU prime, change in U evaluated at A and B. Now there are two ways of interpreting this equation. We're going to say that this, of course, is equal to 0 at functions that extremize the functional E of U. But there are two ways that we can think about it. We can say that E of U is stationary with respect to all tiny changes delta U that vanish at the endpoints. In that case, we get that the changes vanish at the endpoints by assumption. This term is 0. If this has to be 0 for all delta U that are tiny, then we have to, when we have a differential equation, which is minus P U prime prime plus QU is equal to 0. So that's a differential equation, and we can write that as L on U is equal to this. And you may have noticed that this equation is automatically in self-adjoint form. That's why mathematicians make a big deal of self-adjoint form, namely when you take your energy-like functional, ask for an extremal, the differential equation you get is automatically in self-adjoint form. If, on the other hand, you say that E has to be stationary, not simply with respect to all U's that vanish at the endpoints, but with respect to all tiny changes in U's, whether or not they vanish at the endpoints, then we get this differential equation plus the boundary condition that P U prime delta U BA should vanish. Or equivalently, that P of A U prime at A delta U at A minus P of B U prime of B delta U of B should equal 0. And that tells you then that P of A U prime of A is 0 and P of B U prime of B is equal to 0. These things are called natural boundary conditions. Natural boundary conditions. And if P of A and P of B are both non-zero, or if either one is non-zero, then what we get is that U prime of A is equal to 0 and U prime of B is equal to 0. So assuming that the P's don't vanish at the endpoints, then the natural boundary conditions imply what are called Neumann boundary conditions. So there are two sets of boundary conditions, the Neumann ones and then the Dirichlet ones. Anyway, this is Paul Neumann, who lived quite a long time, unlike Abel. He lived from 1832 to 1925. That was a good time to die because it was the roaring 20s and before the crash in 29 and the Second World War and the genocide and all that. So he picked his interval very well. So that's why we have these particular natural boundary conditions, and also why we have this definition of a self-adjoint differential operator, namely minus d by dx, d of x, d by dx, plus q of x. So this is a second order differential operator. And this is a differential operator of this form is said to be formally self-adjoint. We'll say what really self-adjoint is presently, but I think we may have run out of time. Actually, no, and I don't want to keep it here longer. Yes, we just went 1 minute over. Is there a question? All right, if there's no question, let's end it. Is anybody starving?